Hello students. In today's lecture, we will study gravitation chapter and we will cover NCERT section 7.3 and we will also solve an example 7.2. This is disclaimer, learning objective. So students, by the end of this lecture, you will have a solid understanding of what we will cover today. So the concept is universal law of gravitation. So in today's lecture, we will cover first 7.3 universal law of gravitation. After that, we will cover example 7.2. So today we are going to explore the fascinating concept of gravitation. Our main aim is to understand the universal law of gravitation, which is a fundamental principle in physics. This law helps us explain how objects in the universe interact with each other through gravitational forces. So here question arises, what is universal law of gravitation? This law tells us that every material body in the universe attracts every other body with a force which we denote as F. This attraction is a fundamental interaction that governs the motion of planets, stars, and galaxies. Take a look at the figure illustrating the gravitational force between two masses. First, capital M, second, small m. So force F is directly proportional to the product of their masses. So the force F influenced by the two main factors. First is directly proportional to the product of masses involved. This means that the greater the mass, the stronger the gravitational pull between them. The second factor affecting the gravitational force is the distance between the two bodies, that is R here. So the force is inversely proportional to the square of distance between them. So between the two bodies, the distance is r, small r. Alright. So inversely proportional to square of the distance between them. This means that as the distance increases, gravitational force decreases rapidly. This relationship is important for understanding how gravity operates over vast distances in space. Alright, so here two things are important. First, directly proportional to product of their masses. It means F is directly proportional to capital M into small m. And the second is F is inversely proportional to the square of distance between them. Alright. Now we will study the mathematical formulation of the law of gravitation. So here we will understand how this fundamental force operates between two masses. We will start by considering 2-point masses, which are essentially objects that have mass but occupy a very small space. This setup will help us simplify the problem and focus on gravitational interaction between them. So consider 2-point masses M1 and M2 separated by a distance r. Look at here. Two masses m1 and m2, and the distance between small r. The important point here is this: we will measure the distance between center to center of the bodies. Alright. So magnitude of gravitational force, that is capital F, is directly proportional to product of masses, that is m1 and m2. This means that as either mass increases, the gravitational force between them also increases. Alright, because F is directly proportional to masses. This relationship is a cornerstone of Newton's law of universal gravitation, which we will explore further in subsequent discussions. So, let's start by discussing the relationship between force and distance. The gravitational force, denoted as capital F, is inversely proportional to square of the distance between two bodies, or we can say between two objects. This means that as the distance increases, the force decreases rapidly. Mathematically, we express this as F, capital F, is inversely proportional to r square, square of r. So, combine this relationship with another important factor: the masses of the object involved. The gravitational force is not only dependent on the distance but also on the masses of the two objects. Alright. So F is directly proportional to m1, m2 and inversely proportional to r square. So by combining these ideas, we arrive the expression that the force is proportional to product of masses divided by the square of the distance between them. So to removing the proportionality sign, here we will add a constant. So here we introduce the universal gravitational constant capital G to complete the equation. The full expression F is equal to G into product of masses, that is m1 m2 divided by r square. This is known as universal law of gravitation, and it's a fundamental equation in physics. So this equation 7.5 is very important. In upcoming lectures, we will use this expression to solve problems. Alright. Where G is called universal gravitational constant, which is a fixed value that allows us to calculate gravitational force accurately. Now, we will study the characteristics of gravitational force. This force is fundamental to how objects interact in the universe. The first characteristic of gravitational force is that it is always attractive. This means that it pulls objects towards each other, never pushing them apart. This is why planets orbit stars and why objects fall to the ground on the earth, because of attractive nature. Next, the gravitational force is central force. This means that it acts along the line joining the centers of two bodies. Alright. So imagine a straight line connecting the center of the earth to the center of the moon. the gravitational force acts along this line. So this means it acts along the line joining the centers of the two bodies. All right. This concept, central force concept, means that the force is directed along the line joining the centers of two bodies involved. This is important because it helps us to understand the predictable paths like orbits, celestial bodies. Now, let's talk about the Newton's law of gravitation, which is applicable to point masses. A point mass is a simplified model where we consider an object's mass to be concentrated at a single point. This simplification helps us to calculate gravitational interactions more easily. Alright. So a point mass is a theoretical concept, assumes no size or shape, just mass concentrated at a point. This idea is useful in physics to simplify complex systems and focus on the gravitational interactions without worrying about the object's dimensions. Alright. Now we will study the vector form of the law of gravitation. This is important because it allows us to analyze the direction and magnitude of forces between the two masses in a more precise way. So let's start by considering two masses m1 and m2. Be r1 and r2 are the position vectors respectively. The gravitational force on m1 and the gravitational due to m2 is directed along the r vector. This is directed along the r vector. Now we define the vector distance from m1 and m1 to m2 as r equal to r2 minus r1. This is r2, the position vector, and r1 is also position vector. r1 shows the position of mass m1 and r2 shows the position of mass m2. Alright, and the difference is r. r is equal to r2 vector minus r1 vector. This equation is fundamental because it gives us the exact vector pointing from one mass to other, which is essential for calculating the gravitational force. Alright, so vector distance from m1 to m2 is r equal to r2 minus r1. And unit vector from m1 to m2 is r cap is equal to r vector divided by mode of r. This unit vector is important because it provides the direction of the force without considering its magnitude. By normalizing the vector r, we ensure that r cap has a magnitude of 1, making it is a pure direction vector. Now continuing with a vector law of gravitation. So now let's focus on the force exerted on m1 due to m2. Force exerted on m1 due to m2. This force are denoted as F12. F12 acts in the direction of unit vector r cap. The equation for the force F12 is equal to G m1 m2 divided by r square r cap. Here G is what? G is the gravitational constant. M1 and M2 are the masses and r is the gravitational R is the distance between them. Distance between the masses M1 and M2. Center to center. Alright. So this is the force. And this is important term. So, or we can say, we can express the gravitational force as F12 is equal to G M1 M2 divided by R mod of R cube into R. This form emphasizes the vector nature of the force, where R is the vector pointing from M1 to M2. The magnitude of R is cubed in the denominator, which ensures that the force's direction is accurately represented. This equation highlights how the force's direction is aligned with the vector R, providing a complete vector description of gravitational interaction. Alright. Continue with vector from the law of gravitation. So let's start by considering two masses M1 and M2 and how they interact with each other through gravitational force. So now we see the force on M2 due to M1 denoted as F21. This force acts in the opposite direction of the unit vector r cap, which points from M1 to M2. The equation F21 is equal to G M1 M2 divided by R square into minus R cap. This shows that the force is proportional to the product of masses and inversely proportional to square of the distance between them. Notice the negative sign indicating the direction is opposite to R cap. So the figure here helps us the visualization the interaction. So look at here, R1 position vector of mass M1, R2 position vector of mass M2, and R is the difference. Alright. Or we can say the expression for gravitational force F21 is equal to minus G M1 M2 divided by mod of R cube into R, which is displacement vector from M1 to M2, and the magnitude of the force is scaled by the cube of the distance, a mod of R cube, ensuring the directionality is maintained. This equation is essential for understanding gravitational interaction in vector terms. Continue with vector law of gravitation. So as we discussed previously, the gravitational force exerted by body 2 on body 1 is equal to magnitude, we can say is equal to magnitude but opposite in the direction to the force exerted by body 1 on body 2. This fundamental principle of Newton's third law of motion. This is a fundamental principle of Newton's third law of motion. So the figure here illustrates this concept, showing the force on mass M1 due to mass M2 along the vector R, which is the difference between the position vectors R2 and R1. So the equation F12 is equal to minus F21 tells the idea that the force on body first due to body second is equal and opposite to the force on body second due to first. This negative sign indicates the opposite direction of the forces. Understanding this equation, and it is an important concept. Now we will study the properties of gravitational force. Gravitational force applies to all masses in the universe. Alright, or we know gravitational force is always attractive. This means it pulls masses towards each other. In calculations, this is often indicated by a negative sign. It's important to empathize that the force never pushes objects apart. It always pulls them together. Next, the gravitational force is central force. This means it acts along the line connecting the center of two interacting masses. Imagine a straight line drawn between the centers of two objects. Gravitational force acts along this line, pulling them towards each other. Next, gravitational force obeys Newton's third law, which states that uh, for every action, there is an equal and opposite reaction. This is represented by equation F12 is equal to minus F21. The force exerted on body first due to second is equal to minus of force exerted on body second due to first. Alright. This reciprocal action is a fundamental aspect of gravitational interactions. Now, we will study the superposition principle in the context of gravitation. This principle is important. It helps us predict the behavior of complex systems by considering the forces between individual particles. So, let's start with statement. For a system of multiple particles, the total gravitational force on any single particle is the vector sum of forces from all other particles. This means we cover both the magnitude and the direction of each force, which is essential for accurately determining the net force acting on a particle. Law of gravitation is often applied to a point masses. In reality, we frequently deal with extended bodies. This distinction is significant because it affects how we calculating gravitational forces in practical scenarios such as when we dealing with planets or large celestial bodies. So, to understand this, consider a collection of point masses m1, m2, m3 and m4. Alright, the gravitational force on m1 is the vector sum of the forces exerted by m2, m3 and m4. So this figure helps visualize how each of force contributes to the total force on m1, reinforcing the concept of vector addition in gravitational interactions. Alright, so here the force due to first, force on mass second, similarly force on mass third and force on mass 4. So this is the illustration of superposition principle. Now continue with superposition principle. So we see that the total gravitational force on mass m1 is due to the combined effects of masses m2, m3 and m4. The figure illustrates this concept by showing how each mass exerts a force on m1. Alright, and these forces add up vectorially. Point clearly how the forces are represented and arrows indicating both magnitude and direction. So F1 is equal to F12 plus F13 plus F14. Force on body first is equal to force on body first due to second plus force on body first due to third plus force on body first due to fourth. Each term represents the forces from one of the other masses, emphasizing the additive nature of forces in superposition principle. So finally, we can say each component of the force is calculated using Newton's law of gravitation. For example, the force between m1 and m2 is given by gm2 m1 divided by r21 square into minus r1 2, where g is the gravitational constant and r21 is the distance between the masses, and minus r1 2 is cap is the indicates the direction of the force. So this equation shows how the each mass contributes to the total force on m1, reinforcing the superposition principle. So just put the values of F12 plus F13 plus F14. So the equation, the force on body first is this one. All right. Continue with the superposition principle. So let's see here the total gravitational force on a point mass denoted as F1 is the vector sum of forces exerted by other masses. The equation shows how each force component is calculated using gravitational constant g. The masses involved and the distance between them. Notice how each term in the equation corresponds to a different masses exerting a force m1. So force on m1, force on second part m2, and force on m1. The force is on m1 by other masses. F12 is the force on m1 due to m2 and so on. R21 is the magnitude of displacement vector from masses m2 to m1 and so on. Example 7.2. 3 equal masses of m kg each are fixed at the vertices of an equilateral triangle ABC. A. What is the force acting on a mass 2m placed at the centroid G of the triangle? B. What is the force if the mass at vertex A is doubled? Alright. So here you have to find out the force in both cases. And G is the here centroid. So let's see the solution. Given 3 equal masses of m kg at vertices A, B, C of equilateral triangle. Mass of 2m kg at centroid G. AG equal to BG equal to CG, that is equal to 1 meter. And G is the universal gravitation constant. Alright. So let the forces exerted by masses at A, B and C be FGA, FGB and FGC respectively. This notion helps us keep track of which mass is exerting which force. Now we will calculate the force exerted on the mass at G due to the vertex at A. This represented as FGA is FGA is equal to GM 2M divided by 1 square G cap. Alright. So FGA is equal to 2GM square G cap when we solving above equation. Now force exerted on G due to B is FGB equal to GM 2M divided by 1 square into minus I cap cos 30 minus J cap sin 30 degree. So when we resolving the forces, force here the force on G due to B. So this is minus I cap cos 30 and minus J cap sin 30. So the force on GB is equal to GM square into minus root 3 by 2 I cap minus 1 by 2 j cap. Alright. So let's start by considering the force exerted on the mass at the centroid due to one of the masses at the vertices, specifically by mass c. So it will be FGC is equal to GM 2m divided by 1 square into 1 I cap cos 30 minus j cap sin 30 degree. So here this is the force exerted on G. Alright. When we resolving the component, so I cap cos 30 and minus j cap sin 30. So it will be FGC equal to 2gm square into 1 root 3 by 2 I cap minus 1 by 2 j cap. So resultant force is FR equal to FGA plus FGB plus FGC. Alright. So FR is equal to 2gm square j cap minus 2gm square j cap plus 0 I cap. Notice how the forces in the j cap direction cancel each other, leaving no net force in that direction. So FR equal to 0. This means that the force from the three vertices perfectly balance each other out at the centroid, resulting in no net force on the mass 2m. This is important to understand the resolution of forces. So here, second, force when mass at A got doubled. So the force exerted on G due to the mass at vertex A given by the Newton's law of gravitation. The formula is F equal to G m1 m2 divided by r square. Here m1 and m2 are the masses involved and r is the distance between them. Alright, so just put the values in the formula and you will be get the FGA prime. So FGA prime is equal to 4gm square j cap. This is new force exerted by the doubled mass at A on the mass at G. The j cap indicates the direction of the force which is along the line connecting A and G. Alright. Now force at B and C will be same as before, since there is no change at these 2 points. So FGB prime is equal to FGB equal to 2gm square into minus root 3 by 2 I cap minus 1 by 2 j cap. So the force components in I cap and j cap directions. Similarly, the force at point C is F prime GC remains unchanged and it is equal to FGC. So this equation 2gm square into root 3 by 2 I cap minus 1 by 2 j cap represents the forces components. Point out that symmetry in the I component which is positive and indicating direction. Alright. Now let's calculate the resultant force acting on the mass at the centroid. So we begin by summing the forces due to each mass at the vertices. So the resultant force denoted as FR prime is equal to the vector sum of the forces from each vertex. So FGA prime plus FGB prime plus FGC prime. So here it will be FR prime is equal to 4gm square j cap plus 2gm square into minus root 3 by 2 I cap minus 1 by 2 j cap plus 2gm square into root 3 by 2 I cap minus 1 by 2 j cap. Alright. Simplifying. So FR prime is equal to 4gm square j cap minus 2gm square j cap. So FR prime is equal to 2gm square j cap. This indicates that no net force is directed upwards along the y-axis. So initially the net force is 0 due to symmetry, but when one vertex is mass doubled, we get a net upward force equal to 2gm square j cap. Now we will study how gravitational force work when dealing with objects that are not just point masses like the Earth. This sets the stage for understanding more complex gravitational interactions. So gravitational force between an extended objects like Earth and a given point mass, the standard gravitational force equation, that is gm1 m2 divided by r square, is not directly applicable. This is because we are dealing with an object that has mass distributed over a volume, not just a concentrated at a point. So each point mass within the extended body exerts its own gravitational force on the given point mass. This means that instead of one simple force, we have multiple forces acting from different parts of objects. It's important to point out these forces are not aligned in the same direction. Since these individual forces are not aligned, we can't just add them up directly. So we need to add them vectorially. This means considering both the magnitude and direction of each force to find the total gravitational force acting on the point mass. Hence, when we dealing the extended objects, we must consider the vectorial addition of force to determine the total gravitational force. Now we will study how two important scenarios involving gravitational force exerted by a hollow spherical cell. Understand how these forces behave when a point mass is placed in a different positions relative to the cell. So in the first scenario, we have a point mass located outside a hollow spherical cell. As you can see in the figure, the point mass is external to the cell. This setup is important for understanding how gravitational force act in such configuration. So gravitational force acting on a different parts of the cell. So different parts of the cell exert forces on the each point mass. So we can categorize these factors into two main types. The first type includes forces that point toward the line joining the center of the cell. So the second type of the forces acts perpendicular to the line joining the center of the cell. These forces are interesting because they have a unique property. And all forces that act perpendicular to the line cancel each other out when summed together. This cancellation is a key concept because it simplifies the analysis of net gravitational force on the point mass. All perpendicular forces cancels out when added together. So when a point mass is outside a hollow spherical cell, the net gravitational force it experiences are direct toward the center of the cell. Only the forces pointing toward the center remain, creating the final net force. Now we will study some fascinating results about gravitational forces on a hollow spherical cell. We will understand how two key outcomes related to the gravitational force exerted by such a cell. So second is consider when a point mass is placed inside a hollow spherical cell. As you can see in the figure, we have a hollow sphere with a point mass located inside it, small m. This setup is important for understanding the unique gravitational interaction that occur within the cell. So when a point mass is inside the hollow cell, it experiences a gravitational forces from every part of the cell. This is because each segment of the cell exerts a gravitational pull on the mass. So these gravitational forces act in various directions due to the spherical symmetry of the cell. Each region of the cell pulls the point mass in different directions, creating a complex interplay of forces. This diversity in the force direction is a key to understanding the net effect on the point mass. So these gravitational forces cancel each other, resulting in zero net gravitational force on the point mass. So let's summarize what we studied. So the universal law of gravitation is a fundamental in physics, stating that every object in the universe attracts every other object. This attraction is proportional to their masses and inversely proportional to the square of the distance between them. This means that the larger mass is stronger the force, and greater the distance, weaker the force. The mathematical expression of gravitational force, it's given by the formula F is equal to G into m1 m2 divided by r square. Here F is the gravitational force, G is the universal gravitational constant, m1 m2 are the masses of the two objects, and r is the distance between their centers. An important characteristic of gravitational force is that it is always attractive. This means it pulls objects towards each other, and it acts along the line joining the centers of two bodies. This is known as central force. In vector form, gravitational forces between two bodies are equal and in magnitude but opposite in the direction, represented as F12 is equal to minus F21. This means that the force one object exerts on another is equal and opposite to the force exerted back. It's a perfect example of Newton's third law of motion. For every motion, there is an equal and opposite reaction. This symmetry is a fundamental aspect of gravitational interactions. So, for multiple particles, the total gravitational force on a particle is a vector sum of individual forces from all other particles. For a hollow spherical cell, external points experience forces as if the cell's mass was concentrated at its center. This is important simplification that helps us understand gravitational interactions with spherical objects like planets. For a point outside hollow spherical cell, all external points experience force, and gravitational force behaves as if all the cell's mass is concentrated at its center. Now, importantly, these laws were initially formulated for point masses. They can be extended to larger objects. By using vector addition and symmetry principles, we can apply these concepts to more complex systems, allowing us to analyze gravitational forces in a wide range of scenarios. Alright. Now we have some practice questions, and this is homework for you. First, a planet of mass m exerts a gravitational force F on a satellite of mass m at a distance r. If the distance is doubled, what will be the new gravitational force? Second, calculate the magnitude of gravitational force between two masses of 4 kg and 9 kg placed at 3 meters apart. Third, 3 point masses of 2 kg each are placed at the vertices of the equilateral triangle of side 1 meter. In which direction will the net gravitational force act on a point mass placed at the centroid of the triangle? How will the gravitational force between two objects change if the mass of one object is tripled and the mass of the other object is doubled? Fifth, a point mass is placed at the center of a hollow spherical cell. What is the net gravitational force experienced by the point mass? Alright, so these are practice questions and this is homework for you. I hope all concepts are clear. Thank you for your attention.